All good to go?
All good.
Yeah.
So, welcome everyone to tonight's version of our FRC workshops for Australian teams. Hopefully we're going to welcome some other people from around the world to be watching tonight. I think we're in for a real treat. Tonight we have James Kirby with us. He is from the Blue Flamingos, team 7561. Jay is, so I will turn it over to you and off we go. Hopefully we're going to welcome other people from around the world to be watching tonight. I think we're in for a real treat. Tonight we have James Kirby with us. He is from the Blue Flamingos, team 7561. Jay is, so I will turn it over to you and off we go.
Cool, yeah. Good afternoon, everyone, and welcome to the seminar. I'm giving a presentation on simple mechanisms, not specifically for FRC. Much of this can be applied to the first tech challenge. So this presentation is broken up into a few components. The first is basics of the mechanisms and the many different ways you can turn different motions into others. Then it will go into some more
practical. James, I think you maybe have YouTube going somewhere else because we're getting a huge echo.
So to make this presentation is broken up into components. The first is I'll take a look. Basics of the mechanisms and the many different ways you can turn different motions into others. Then it will go into
James, I think you maybe have YouTube going somewhere else because we're getting a huge echo.
I do not believe so. That looks all good to me. Is that any better?
All right, let's try again.
Yes. Yeah, I'll go again from the beginning.
That sounds much better. Let me just say welcome again.
Yep.
And we're looking forward to what you have to say.
Cool. Yeah. Good afternoon, everyone, and welcome to the seminar. I'm doing a presentation on simple mechanical mechanisms, not specifically for FRC, also can be definitely translated across to other things such as the first tech challenge. This presentation is broken up into a few parts. The first is basics on how to turn different motions into others, then some more practical uses for these, and then some analysis of machines that I've picked out as great examples of proper use and combination of these mechanisms. Cool. So a mechanism is an electromechanical device in FRC, particularly to achieve a game task, they can be considered, because if it doesn't do that, then there's not much point of it being there. A good mechanism will do its job whenever you want it to without you having to nanny it. So efficiently, hopefully as fast as possible, and yeah, most importantly, reliably. Just because there is a task doesn't mean there is only one way to do it. There are numerous ways to do a single thing, and that is why we have such diversity in the robots created for FRC and FTC. And say you select the perfect mechanism, it's not really a thing. You can have very good mechanisms towards it, but it's how a team implements it on the machine makes it just as effective, which is why you have teams that are fully CNC machined with very elaborate designs being outclassed by simpler robots that maybe don't have as much money behind them because the way they're designed is better implemented for the task at hand. So we'll start off with linear motion. This is actuation along an axis, no curves or bends, just straight line. There are a couple of reasons why this is beneficial. Number one, a linear mechanism generally has a larger contact area between two or more moving parts. This means it's generally more durable. This is very much down to how it's built, but that can be one reason for it. If you wish to stow a mechanism in a particular way, they can be almost the only way to do it. Obviously, in FRC, a lot of the time one wishes to exit and re-enter the frame perimeter. So the way in which you do this obviously has to take up as little footprint on the machine as possible. A good example of this in the bottom right-hand corner here, we have Spartan Robotics 2017 machine. Their intake extended out and retracted on linear slides that sort of wrapped around their hopper and ball mechanism. This is a great example of that used effectively, as any sort of folding way would have drastically reduced their size of their hopper that they could store. Another good example is, for reasons of this, is the speed at which you can actuate a mechanism. If it only goes in a straight line, you only have to deal with the forces in a straight line, and therefore they can be better predicted for and handled. Generally, you can give more force this way or higher speed, and thus also less ways that it can fail. The first way to get linear motion is with stored energy in the form of a spring or an elastic system or something similar. Probably the easiest way to get linear motion that isn't controllable as such, or at least you need access to be able to control it. But obviously out of this, it's very simple. You can't really go wrong until it fatigues or fails. The main focus is to have a controlled release, as adding energy back in can happen over a longer period of time, as well as have a more complex mechanism behind it. An example shown is a simple latch mechanism that has a spring pulling back another latch. But the main bit to focus on is the handle that releases that latch mechanism. That's a very simple way to do it. You can actuate that with a motor or with a cylinder, and the spring can be released. That can be scaled up to pretty much any size as long as one builds it well. Or another way is to just have a gear that sort of winds and retracts back a mechanism, but has some teeth missing. So when it gets to that point with the teeth, it can spring back out. Not used very often because it can damage the gears, because the teeth would then hit back in contact. But if you have another option, that is a way of doing it. Generally, in FRC, springs and whatnot are only used to supplement other mechanisms, because to extend would require complex mechanisms that you could just devote that weight and power directly to it. But it is good to know, particularly for a lot of energy released in a quick amount of time, such as to launch a singular object. A good example of this would be in 2014, where large balls were often shot either with pneumatics, but a lot of people or a lot of teams did use springs and elastics, and latch mechanisms like this were quite common. All right, so probably the most common way to get a linear motion is with a pneumatic cylinder, because you put air in this one this way and it will go that way, reverse it and it will go back the other way. So it is very, very simple and very reliable. And you can get ever more increasingly large pneumatic cylinders to have ever increasing amounts of power as well and durability. Pneumatic cylinders, besides paying a lot and getting complex ones, are only two position. They are either fully extended or fully retracted. But this is not always a bad thing. Often it can be quite good, as it means it will go to that position or back without obstruction, which means there are no sensors required, there's no feedback loop. It just sort of works. And so if one is extending or retracting an intake, a pneumatic solution is often ideal because it will go to those two positions with as least complexity as possible at the effector side. Pneumatics do require a lot of complexity at the back end, but that can be handled and sort of contained and dealt with separately. So pneumatics are mechanically reliable and can be powerful. And yes, so definitely consider the use of those. So the second way to do this would be to use motors. So there's lots of reasons to use motors. One is the overall complexity, I would say, is reduced with an electric solution, because there are lots of components that are required to do a pneumatic solution within the rules of FRC and just flat out not permitted in FTC. The oldest way to turn a rotary motion into a linear motion would be to use a cam. So if you look at steam trains, they do this sort of in reverse. They take a linear motion and turn it into a rotary motion at the wheels from the cylinder with the massive connecting rods there. This can be done in the reverse with no issue at all. It's very, very simple, very, very easy to make. But the disadvantage of this is that it's generally not very strong. And as the cam rotates, the speed at which the linear motion is output will change. This can be beneficial because you have more power at when it gets straighter and less power at the start, if that's what some ideals. Not used very much for this reason, not very durable and a bit unpredictable. On the right here, we have probably the most common one, a chain sprocket. This can be a belt or pulley, or any other combination of similar idea, but the idea is you have a flexible solution wrapped around two or more circular hubs, sprockets, pulleys, and that's there. If you have straight sections, it will move in a straight line. And this can be quite precise because you can easily attach sensors or encoders and have known positions for things, and can be quite strong output, a decent amount of power. But there's also ways it can fail, and they're generally quite difficult to construct well, because if you have a long run of chain or belt, you'll pretty much always have slack. And so there must be other accompanying components to rigidify that mechanism, which adds weight, which adds complexity, more ways it can fail. But on its own, a chain sprocket mechanism is quite a light and probably a better way, especially over a cam, to get a simple linear motion out of an electric motor. Two more ways here, a bit more complicated and expensive. A rack and pinion do a similar job to a chain sprocket. Uses a spur gear that has a matching spur profile on a rack. So the idea is that when the gear turns, the rack will move, and vice versa. This is imaged on the left. This is very, very strong, very durable if done well, and probably, the most durable, the strongest way to have a linear mechanism with an electric motor, but it requires expensive or particularly difficult to manufacture gears and racks if you cannot find them off the shelf. And they must be precision mounted. They have to mesh very well. Otherwise you'll get slack, teeth will skip, teeth will break, and then it becomes even more expensive. This can add weight, and the rack and gear themselves are often steel. Otherwise, just don't use them if they're not steel, unless it's an aluminium gear, which is acceptable, which is heavy. And especially, weight is not a good idea. So another alternative on the right here are screws. These are often used if you look at a lathe, if you look at a mill, or any high-end CNC machine. Will have screws because they are very precise and very high power, and you can very easily remove slack with this mechanism. Because of the way the thread is cut, you can end up with a lot of turns for very little linear motion, which means a lot of power out the other end. The velocity ratio is very high, and therefore quite a precise amount of movement, because the difference between the turns and the movement is as small as possible. So this is very good for a lot of situations. It's very compact at the end of the day, but the threads themselves are fairly fragile if you try to put too much load on them. They're quite expensive. It's very, very difficult to make these oneself. And this is essential, you must have thrust bearings on either end of the screw, because there is a lot of axial force along the axis of the thread, which regular bearings probably can't handle in most situations. These thrust bearings are more expensive and harder to get in, I guess, FRC standard sizes. And I don't think one will be able to find a thrust bearing with a 1.5-inch hex cut through it. So one must look for other options there, but definitely something good to consider. I've seen them used for extending mechanisms out the front of a robot. I'm pretty sure Hastings Heroes did that in 2019, and also used on an elevator by the Blacktown Girls robotics team, which allowed them to have not a whole lot of motor power to move quite a large and heavy system. Cool. So, this is all good and well, but how do you actually do it in a real world? Probably the most reliable, the strongest, the best, simplest way to get it is from a linear actuator. So these actually use a thread like was previously described, but very nicely and compactly made. So you end up with a simple off-the-shelf solution that you get a lot of power out of, that, you know, can have built-in limit switches, so you don't even have to sense to cut off the motor. It can do it itself. Easily hoist over 100 kilograms. Rigid mounting. The only cost of this would be they're decently expensive. You can get good ones for about $40, $50, but I guess way the cost of making it yourself. And can be fairly heavy. And you have to sort of hack in, if you can't find it, hack in a FRC legal motor. But if one can do this, it pretty much can't go wrong, given that it's done well. So yeah, that's definitely keep that in mind if one's trying to make something heavy move in a straight line. On the other end of the scale, if you want just to move a mechanism in a straight line for a cheap price, an easy way that isn't as complicated, or want to have a more compact or different mechanism that you can't use a linear actuator, draw slides are a very, very good way to do this. Our FRC robot, my team in 2019, had 13 draw slides across it, 8 for the climber, 4 for the intake, and 1 for the column mechanism. For $7.50, you can go to Bunnings and get a pair of 300mm draw slides that can support 45 kilograms across them. The only downside to this is that it's possible to pop out the sections of a draw slide. This can be solved by gluing some bits in, because it's designed to pop out. There's some plastic bits that are able to manually release that. But with appropriate time and handling, these can be a very, very useful, compact, and particularly cheap method. These individual draw slides are so cheap they don't count towards the bill of materials when that was still a thing. They are a bit heavy though, because often they're made of steel because of the sheet construction. The most compact and the most durable method of linear motion is a tube inside a tube, particularly circular tube. If the inner diameter of the outer tube matches the outer diameter of the inner tube, they will slide very nicely without bearings if you lubricate it and if it's light enough. On the bottom left, you can see pictured part of the CAD model of our team's color mechanism. It uses a pair of aluminium tubes, again, bought from Bunnings for $5 a meter, just inside each other, some lithium grease, slides beautifully. Very good way to do it, considering there's not too much load. Super, super light. The entire mechanism probably weighs as much as the pneumatic cylinder, if you ignore the bag motor and gearbox on top. On the other extreme end of the scale, you get teams such as PPT Bots, which is 6986, and 148, the Rover Wranglers, and the Chimeras, which I've got their number. We have carbon fiber tube for large elevator mechanisms. Super light, super strong, very difficult to manufacture. If you know how to do it, you know how to do it. But to give an idea of the caliber of team required to make this, you can see at the front, their gearboxes are cast machined solid blocks. So not something for, I doubt many Australian teams will be able to do that, but it's definitely a very good way, and lucky you if you're able to achieve that. Another common way to do an elevator is bearing blocks. These can be on the outside of a tube or inside of a tube. So you can either buy them or you can make them. And Mark sells ones that will ride directly onto 2x1 inch extrusion or 50x25. This allows big elevators to be made. We used them in 2019 with a very large, heavy elevator, and they worked perfectly. Entirely with hand tools, that elevator was made, and we didn't really have any issues with it. So obviously, not many teams can make those carbon fiber elevators. This will be the path for that. If the bearings blocks are inside the tube, you can end up with a sort of telescoping style, which is very compact. Obviously, weight will increase there, but all good ways to do it. So in the real world, these mechanisms are all great, but none of them are perfect. There's a little square at the bottom where you see 4 qualities: how cheap it is, how light it is, how strong it is, and specifically for linear mechanisms, how many times its original length can it extend. You cannot have high amounts of all 4 of these. And in reality, you can't have something that's cheap, light, and strong. But this is in relation to other linear mechanisms. If you want to have one over another, there will be a cost. You can make a very nice bearing block elevator that happens to be a bit heavy. You start cutting holes in it, or it loses its strength. And you get an water jet cut, well, then it's more expensive. And even the carbon fiber elevators, they're very strong, they're very light, high extension ratio, but they are very expensive to manufacture and also dangerous. Carbon fiber should not be cut without proper respiratory gear. So that's definitely something to keep in mind. No solution is perfect. Just because they have more money and to be able to do that does not mean it's a better solution than what one can consider with a different option. So here's some examples from my team. On the left, you can see the tube mechanism I spoke of before. Very simple, and it was made in just a couple of hours. Again, even if you're not going to immediately use it, I very much recommend picking up some aluminium tube from Bunnings because you can end up doing some pretty interesting and light stuff with it. And on the right here, which I'll play in a second, is the draw slide stacked climber that we end up using. It's 4 draw slides stacked on each other and then rigged like an elevator. So it extends quite a bit beyond its original length, as you'll see. And yeah, this was quite cheap way of doing the climber. And it ends up being quite durable. There's a little bit of flex, and we do aim to solve that with some other ways. But it's very, very compact. These draw slides are very small. And yeah, so even one can solve the problems of the draw slides popping out, definitely a good way to make a climber-like mechanism. But do be sure that the climber rope does not snap. Here is the intake from our 2019 robot in the prototyping stage, so please forgive the messy wiring. One can see here, one problem with the draw slides, as I said, is they pop out. On the right-hand side picture, you can see we have on both sides 2 draw slides. One of them is vertical and the other one is horizontal. This is so that the strength of each would cancel out. And so for low down side hits, the bottom draw slides can tank that. But for all the vertical stuff for picking up the balls and running over something, those vertical draw slides can take it and save the bottom ones. And the bottom ones are upside down so that they're less likely to pop out with the vertical impact. This has worked really, really well. We carry the robot by that mechanism extended, which should be a testament to just how strong these draw slides can be when used correctly, because we're pretty much at the weight limit. And yeah, that's a great way of doing that. So now we'll start on rotary motion. This is everything else, as it were, moving around an axis. So why would one go in a circle rather than a straight line? Or it tends to be mechanically simpler. There's fewer bits involved. Particularly, you can just ignore bearings and use bushings, and then there's really nothing to it. It's just some bits rubbing and a motor on the ends. So yeah, there's fewer components required, which can lead to less failure, particularly if one cannot manufacture more complex mechanisms. Quite versatile. There's heaps of applications of levers. Levers require this rotary motion. Is how gearboxes work. Yeah, so you see intakes that are linear, you see them that are rotary, that sort of pivot out rather than move straight out, particularly in this year's game. Generally, it's because it's simpler, and you can sort of adjust the height that it exits out at with on the fly. As I said, gearboxes permit heaps of power output. From comparatively smaller motors, you can reduce the speed to increase the torque, all because you can move in a circle. And so this allows for, in comparison to a pneumatic solution, heaps of power. Big pneumatic cylinders are all very impressive, but if you'd taken one of the new brushless motors and stick it in a tough box, you'd probably get similar amounts of power out of it for about 1/3 the weight, and a lot simpler because you don't need all that air. And the power comes from a motor anyway in the compressor. And then form factor again. If you can't store a mechanism around or sliding in and out, and you have to store it vertically or change the footprints, you can go from flat to vertical. Footprint's a lot smaller at the cost of extra height, but that might be just a trade-off that one has to make. So that's obviously where this would be ideal. So motors output a torque, which is power sort of in a circular motion. So therefore, they're generally the best way to do it. Gears, sprockets, chains, pulleys, belts, they allow you to transmit torque. In the image right, it's quite an old photo. I think it's from about 2003 or 2004. A beautiful machine with wire on pulleys to allow a very complex arm to work, as you can see. Again, gearboxes permit the variance of torque and rotational speed. So it's very versatile output, so you can pretty much pick and choose. And curved rack and pinion mechanisms can allow for rotary motion. That sort of works how you have the rack in a circle and you attach a motor and it turns. There will be a center to that because there is a radius to the rack, and that is, at the end of the day, rotary motion. This can be quite beneficial at the end of the day, as I think we'll soon see. Yes. So on the right here, we have Team Madtown Robotics. This is a photo from their website. At the back, there are two silver curved pieces. These are curved racks to allow, instead of a direct extension, it sort of curves down backward to assist with their climb, which is a very good way of doing it. And on the left here, we have a great example from Team Spectrum's website, their 2011 collection of photographs. This is a picture of, I'm pretty sure, the pink team's arm and whatnot from 2011. It uses various gears, it uses various chains and sprockets, obviously beautifully constructed, but even the linear motion of that arm is powered by a motor turning some gears to get the correct motion out to pull a winch. And the entire arm is rotated by a sprocket because it allows for pretty much infinite positioning within the total degrees of motion. Cool. So with pneumatics, over an electric drive, you have the pneumatics are mechanically simpler to get the rotary so that pneumatics do have advantages over electrics, despite the fact that it's a bit harder to get a rotary motion out of them. The two position control, again, can be very effective, particularly, again, for intakes, because it's two position, no sensors, no fuss, it just works. Yeah, definitely better, because an electric one, you'll have to tell it how to stop. A hard stop works, shouldn't really do it. Sensors becomes complicated, can fail. Pneumatics are great for that, as I said before. So lots of intakes, whether they're rotary or they're linear deploying, are quite a lot of them are pneumatic still, because it's not that difficult to get a motion out of it, not something that can be integrated in. So the two most common ways, one is the reverse what we saw before. This is a cam mechanism where you sort of have a triangle. One of the sides extends, imagine that to be the cylinder, and then obviously will pivot around a point. This is often integrated into a mechanism's mounting and deployment, which makes it very, very common. Good, reliable, simple, all good stuff. On the right, we have something a bit more complicated, but depending on the form factor, it can be lighter or more beneficial. This is a photograph of the Robonauts machine from 2020. They're difficult to manufacture, particularly, again, the racks, hard to make, you can wreck them fairly easily, but if done successfully, as you can see here, the deployment is a very, very small footprint and very, very light compared to attempting to do this. And you can translate a larger linear motion, a smaller linear motion with a lot of force easier into a larger amount of rotary motion compared to having to use a cam with a very small connection. It sort of gets a bit, jumped up when you actually try to make it. So this is a very good method doing that, and there's a reason they chose to do it. So winches. This is obviously using motors. It's just a coil of rope or wire to put tension on that rope or wire. It's a very simple and cheap way of moving a mechanism from a long distance with electric power. One can have a double spool that pulls in both directions, but this can get quite complicated. As you can see here, we've got 3 photographs on the bottom. We have on the left, my team's winch from 2019. And it very, very simple. It's 2 motors in a tough box that has a shaft between 2 plates. We just tied off the rope and hoisted an elevator with an effective weight of about 30 kilos because the center stage was double cascade. Worked every time, never had any issues with it until we put mini sims in it, which was a mistake. On the far right, you can see the 2 ways of rigging up an elevator. I won't go too deep into elevators because that's a whole other discussion in itself. Those are 2 ways to do it. It can become as complex as you want. In the center, we have the elevator of Madtown Robotics from 2019. Complex spools of wire and rigging all within each other. They use wire. You can see there's a lot of power on those 3. I assume they're mini sims on the bottom. Yeah, there you go. So there's many ways you can do a winch. They're very, very useful, but very simple. And it can be quite reliable as long as you make sure you're within the limitations of the rope or wire that you end up using. So here we have 4-bar mechanisms. So these are 4 mechanisms, which one is rigidly mounted generally, not always. Most of the time used because the opposite linkages are in parallel given that those two linkages are of the same length. It's simple to construct, but it's quite heavy, requires a lot of power to move if you're using it for anything of any large size, because you have very long levers at that end. A 6-bar is similar, has an addition to gain extra height. It's very rarely used. If one's interested in that, they can look it up. I think it's used for the VEX robotics competition more often. So in the bottom right, I promise this is the only GIF that I've made. You can see the two green linkages are always in parallel. Two blue linkages are always in parallel because they are of equal sizes on their opposites. On the left is a more novel use of this, which is a from 2011, Team 771, as you can see, in which no sides are rigidly mounted. There's a pivot that's mounted, and using a sprocket and rotating one of those sides, you can get a strange high reach motion out of it. They got elastics, obviously, to take some of the slack off, but at the end of the day, it functions identically. It's just how it's mounted and powered. So here I have two videos of examples of 4-bar mechanisms in two different use cases. On the left, it goes fairly quick. This is Team Miscar from 2018. They had a 4-bar with a sort of rack and pinion actuator to reach up high with quite a large mechanism to place cubes onto the scale. I assume they chose to use this because of the durability of the mechanism, and they don't really need any super accurate positioning. So let's have a look at that. Yeah, so one can see there, they had their 4-bar mechanism maintains the mounting for their intake in a rigid position, so they can actuate that intake and get a easier, precise aiming of that intake. So that's a good way to do it. And on the right, we have a robot in 3 days team that used a 4-bar mechanism in a different way to get a interesting position and rotation of their intake mechanism. Also have a look. So if I play again, one can see here that it started lower at a different angle. The bars in this case are different lengths, which means that the bars will not remain in parallel. But by manipulating this, you can get interesting motions out of it, such as here to store a mechanism in an angle when it's deployed, but vertical when inside. Great way of doing it. This one's pneumatic, up to position. Interesting, nice mechanism. So here's a bit of one that I haven't actually seen used in FRC, but I do believe is useful to know about. It's an acceleration link. This can compound the velocity changing effects of a lever. It's pretty much just two levers linked together. Their effects will multiply as you go along. This one's shown here, a very small actuation of a pneumatic cylinder leads to a lot of movement at the end of the red bauble. The only time I've actually seen this used in robotics applications is for robotic combats for axes to get a large amount of velocity out of it. This can definitely be used to launch a ball in a situation similar to 2016, where you had small boulders that had to be launched. A lot of teams did use pneumatics. I guess they didn't need the velocity that this can provide, but if you ever need it, this is probably a very, very good way to do it. So here is another one more commonly used in robotic combat. A 4-bar mechanism can be used to achieve an arcing motion if the links are different sizes as we saw before. And if you use it right, such as the photograph below, there's a hydraulic cylinder that is powered actually pneumatically, mounted rigidly at the back and halfway up the front linkage. It might be a bit hard to see. I don't know what the resolution is like. This allows a high velocity at the end of the day out the other end. Using different size bars, different arcs can be achieved. And yeah, so this arcing motion, as you can see, the front sort of sticks out. The back link is shorter than the front link. This means that as it pitches forward, the back link will move further than the front link will, which causes the front to sort of flick up. This again, I assume, can be used to launch all sorts of objects in the first robotics competition. But specifically here in a moment, we'll see its effects in its homegrown area to sort of show what a well-made mechanism can actually do for a machine. So one thing to note there, this machine here actually weighs 150 kilograms, and so was the one it was launching over. So well made, you can get a lot of velocity in a very controlled manner out the other end of that. Again, don't flip other robots in FRC. It's not a very nice thing. Not only is it against the rules, but if one ever happens to be launching a large, heavy object, a pneumatic cylinder in an arrangement like this is probably a good way of doing it. Yeah. So I'm about to start a sort of more practical applications in regards to intakes. So I guess if it's appropriate, this would be the time to add any questions from the previous section. This would be a good time to post them in, and I assume I will receive them.
Hi. So we have a couple of questions.
Yep.
The first one is, for the linear actuator, you mentioned hacking in an FRC legal motor.
Yes.
Do you have any particular actuators and motors that you would recommend for doing this?
Right. So linear actuators tend to use sort of weird motors, but they are similar in power to a 550 class motor. Specifically in FRC, there's a Bainbots RS 550, which is permitted. But if you have the opportunity and you're already doing that, you might as well hack in a 775 motor to get a bit more power out of it. I have seen for the case of FTC, pretty much that specific linear actuator had a Neverest motor sort of hacked into it by the Blacktown Girls robotics team. They had a chain sprocket driving from the motor to the screw of the linear actuator. And from my understanding, that hoisted their robot just fine. So for FRC purposes, if you can't make one from scratch or get the Dart actuator, which is an off-the-shelf SIM actuator, a 775 class or 550 class motor will probably be ideal for those.
Excellent. We have one more question at the moment, and this is any pros and cons for wire versus rope for elevators?
Right, that is definitely one for debate. Wire can have a higher tensile strength for the size of it, as well as can often doesn't stretch as much if you use it right. The disadvantage is that you can't do really sharp bends. You have to use larger radius pulleys to slowly turn it around to a different orientation. It's used by a lot of good teams because of its ability to be under high tension and therefore not have any slack. So for precision moving of elevators at high speeds, wire is good. We've only ever used rope on our various elevators because it's just a lot easier to use. It's strong enough. You can get ropes that can hold, 400 kilos. That's definitely enough for all FRC purposes. So unless you know you need wire, just use rope.
All right, thank you. So that's all the questions for now. Go ahead and proceed onward.
Thank you very much. Cool. So now we'll start intakes. Intakes, in my view, are a great example of utilizing these principles in a practical effect. I'll go into a little bit on the different types of intakes that can be used for different game objects, which may be helpful. I know that the FTC season has just started, and I'll provide some examples here. But yeah, let's go straight into it. So balls are very, very common in FRC. I'm pretty sure they're the most common game object to ever be introduced. Pretty hard to grab if you've ever, you get two fingers and try to pick up anything larger than a marble. It would sort of just run away. But it's very easy to roll. So two good methods of collecting a ball, pretty much the only reliable ones, is to have a powered roller on one side and a friction plane on the other, so that you roll the ball along the friction plane to control it. This can be the floor, which is very, very common, to have a large wide roller as shown in the photo in the center down below and on the photo on the right. Often very good because it can be very wide. Balls are often compliant. They can be a bit squishy. You can, handle them a little bit. So that's probably a very popular way of doing it. And the other one is to have two powered rollers either side, so that you're completely forgetting the fact that it's a ball and just launching it or collecting it as it is. Obviously, a ball doesn't care what orientation it is in when collecting, which is a great advantage here. These are good for precision shooting, as it would be, or precision placing. The rollers do not have to be side by side. They can be on top and bottom, as shown on the far right. This is Team 696, the circuit breakers. I know they did fairly well. They actually collected often 2 balls a match, which they shouldn't have. This was back in 2019. This allows, again, just to move the ball. Forget it's a ball. Just get it from one place to another. Obviously, their method was using belts, but rollers, it's the same basic principle. If you're looking for a good example of this with only one roller, Bossley Park Team 6434 back in 2019 had a single belt sort of roller top thing that collected and placed balls, and it worked very well. So very, very simple. Balls are generally the easier object to handle, in my opinion. So you can pretty much, there's lots of ways to do it. I'm not going to go into shooters here. I know that's a completely separate presentation, so I'm not going to steal any of that bloke's thunder. But they can be either 2 or single roller shooters. A single roll one generally functions on the same principle, except just doing it real fast. So you have a single roller in a friction plane that accelerates the ball as it rolls up and shoots off. Or we have a dual roller one, which just forgets the fact that it's a ball and just launches it. That's all I'll go into for shooters, because I know that's a different topic, but that's a good way to deal with balls. So this will be a video of my team back in 2019. We had a single top roller intake with a sort of scoop underneath for collecting the cargo balls last year. This was very, very good at collecting, nice and wide, didn't care about the orientation of the ball, obviously. It was very, very good at collecting, but you'll note it does go fairly quick. When it attempts to shoot the ball into a place to position it, it sort of just drops out the bottom because the roller can only extend so far. And because you are rolling an object, you have to take into account the difference in speed. The larger the object and the smaller the roller, the slower it will go. The roller is actually spun at about 3,000 RPM, but you can see the ball doesn't go very fast. Let's have a look. There we go. So one can see with that, very good at picking up. I do apologize when none of the videos have audio. If there happens to be any music playing, it's entirely possible for YouTube to close the stream down, I believe, automatically. So that's why it's a bit awkward just watching a dead screen, but that's how we got to have it. Yeah, so you can see there, it was a single function mechanism. So it placed and collected with the same one, did not launch the balls very far. And so often we had to sort of pitch up the mechanism to sort of just chuck it in to, and it worked well in the end of the day. But for collection, that's a very good way of doing it. But as we'll see later, for shooting a dual or placing a dual roller mechanism can generally be a good idea. That will come later. All right, cubes. Cubes are very interesting. It doesn't have to be a cube, it can be a rectangle. The power cubes of 2018, as many people will know, were not cubes. They were flatter, they were sort of smaller top dimension, but they were sort of the square on the outside. But for now, I'll discuss how to deal with that in a little bit. You can't roll a cube, or at least it's not very effective to. They sort of have to be slid. But because of the flat sides, they're quite easy to grip. So claws are a decent way of handling this. Proteocephalus did that in 2018 to great success. Team 971, as you can see in the middle on the base, had a claw mechanism to collect and place the cubes, but used dual rollers to intake the cube actually from the ground. So 3 good methods of handling this. Double rollers, because the cube you can grab both sides, it can sort of center itself. The most practical, probably the easiest besides the claw. If I was handling a cube, I'd use 2 rollers. If you look on, the Einstein's field for 2018, all of the robots had rollers, or 2 of them, because as I said, it can auto center a cube and allows you to launch the cube as you wish to in a certain direction. But to handle it properly, it has to have a lot of compliance. Either the whole mechanism has to be a bit squishy, or the wheels have to be a bit squishy. Bossley Park, again, 6434 in 2018, used springs on the sort of hinged either side, and used springs which allow them to very, very easily and quickly collect the cube. The strength of these springs is something to test, depending on the game, depending on the machine. that's definitely probably the most common, the most optimal way to handle it. Claws are naturally compliant. They open and close and will move the object as it is, but can't really self-center, or only to a certain degree, or launch a cube on their own. I've seen claws have a cylinder behind them to shoot the cube, but that's extra complication, while the rollers can do this naturally. Most best used if you're trying to place carefully with rollers to intake, as I said, for 971. But can work. Again, Protobucephalus did it to great success in 2018. Single top rollers or single any rollers can be successful. In 1619, Upper Creek Robotics used it in 2018. The intake is actually a double roller, but it collects off the ground with only a single roller. So for this purposes, I'll consider that. It's quite compliant. They're quite a good team. I would avoid it, but you can do it if you want to be something different. It was obviously a very wide collection. It didn't require, the orientation of the cube didn't matter because it would sort of just bounce on top of it. It allowed for a wide collection, and it didn't center it if that's something that you want. Not my preference, but it was very interesting to see a successful design. So if you want to see a way to do it, 1619 Upper Creek 2018 is the machine for you. This is an interesting method of handling a cube. You can see the front has got two mechanism wheels to sort of pull in the cube, and then it stores it, using those aluminium bits. But this uses effectively double rollers to launch the cube to the scale, which is just two sides of a drivetrain. I thought I would include this as an example of repurposing random bits that you have lying around. I assume this was their 2016 drivetrain that they just slapped onto their 2018 machine. They look quite happy about it, and it worked. The top rollers accelerated a little bit more because they're just directly attached to 775s. But they scored cubes on the top of the scale, which is quite a feat. For people who've been around at the game would know that. So yeah, thought I'd include that to inspire some more interesting designs in the future. All right, so discs. This one's a bit more topical for those doing FTC. They can be rolled or slid, or I guess and slid, depending on the orientation of the disc. So three methods is one, you have a roller on the top and a friction plane, or you want less friction, but it is a plane, or there's always going to be friction, to slide the disc along. This uses the flat surface on the top of the disc to grip it. On the left, we have Code Orange. I'm pretty sure they're Code Orange or Team Orange. 3476 in 2013 had rollers in multiple orientations to center the disc. That was just placed just above the ground, and it pulls in the frisbees. Interesting, good way to do it. Another way to do it is to have one roller on one side of the disc and a friction plane on the other, and roll along that plane rather than slide along. This can be seen in the bottom right. J shooters use this. The idea is you roll it as a circle and use a wheel to roll it. It's very similar to the way balls were done. But this is obviously fundamentally different because instead of sliding, you're using the fact that it's a circle. With a sliding one, it could be a square or a trapeze or a pentagon, it doesn't matter. And then again, if you don't want to care about what the thing is, two rollers, one other side, slide it linearly, launch it, it's good. Again, I won't go too much into shooters because that's someone else's topic, but if you spin something while it's shooting, it will generally lean or move in a direction. Just to launch it can have its benefits, but yeah. So there's more to it than just controlling the thing. Once it exits the robot, there's something to think about too. So here it goes pretty quick. Is an example of a disc collecting intake from 2013 by team, I think the Killer Bees, team 33. These guys were on Einsteins with this machine. It uses a top roller and sort of spade to collect the discs, but then they are stored within the robot with dual rollers. But it's just interesting to see an effective way of collecting the discs. The mechanism is a little bit hard to see, but yeah, there's a top roller and there's a sort of low cutting spade underneath to pick up the objects. So yeah, that's an interesting design. Again, nudge, nudge to anyone doing FTC this year. 2013 is the place to look if you're looking for inspiration. This machine did very well. they did it, obviously they're quite good at making things, so they did it in quite a special way where the shooter was underneath the storage mechanism. But that sort of intake, in my opinion, probably be the best way to go for this year's FTC game. Right, spaghetti intakes. These are vastly more common in FTC compared to FRC. It uses compliant elements that sort of just nudge the object. It really is taking a floppy noodle and hitting something heaps of times a second to make it move in the direction you want. Generally, surgical tubing, cable ties do work. I've seen that. It's pretty much an omni-capable intake. It does not care if it's a cube, doesn't care if it's a sphere or a disc or a beer bottle. It'll all work as long as it fits within the size and it can actually reach it. So that's why in the 2018 game of FTC Rover Ruckus, you had cubes and you had spheres of approximately the same dimensions, but a spaghetti intake was ideal then because it didn't care which one it collected. So that's obviously great use. In FRC though, obviously the game objects are a hell of a lot heavier, and so your wet noodle might work on a marble, but it probably won't work on a bowling ball. So generally it's pretty rare to see. But there was a robot in 2019, don't remember the number, sorry, that had a large apparatus of this to move a cargo ball because it's fairly light, but that was within the robot. It was a very controlled environment. The only time I've seen it used otherwise in FRC is for this year's game, actually, or whatever did get played of it. There is footage of this robot if you wish to see it in action, but it's just not quite good enough, I thought, to put in a presentation. They had 4 sort of sweeping, I think, Roomba-like appendages on the corners of their robot that centered the balls and pulled them in towards just a single top roller and side roller intake. I had not seen this before, and it works quite well considering the balls are fairly light. The faster you spin the intake, the more effective it will be to a degree, because you're hitting it more times a second, you're applying more energy within a period of time. Interesting robot, definitely good design. With bag motors, you can pair 2 of them to one motor controller to have one on each side for any one PDP slot. So that's good to keep in mind. But yeah, if someone wants to make a spaghetti intake for FRC for this year's game, I'll be very, very interested to see it. All right. Before we go into this is some examples of actual machines that I thought notable to discuss. There was a bit of content there, so I guess, if appropriate, are there any more questions about what was just said there?
Hello again. One question. When using belts in the ball intake, is it best to buy off-the-shelf belts or make your own?
Right. So this will very much depend on the application. If you just want it to be easy, use just the same pulleys and belts that you use for power transmission. They are toothed. They got little walls on the side of the pulleys, so they're not going to wander off. There's many ways to, I guess, do it. So again, Bossy Park, they use this tooth belt style, and from my understanding, it never failed them. If you're going to use, long, thin, stretchy belts that you have to cut yourself and make yourself, you have to make sure they don't wander. You have to make sure it's the right tension, but it means your long HTD timing pulleys are quite expensive. To buy long runs of material to make friction belts out of is quite cheap, and allows you to do more complex runs than you can with a tooth belt. And again, at the end of the day, it's probably going to be lighter. So if you're able to manufacture it, good stuff. Make sure it doesn't wander off. There's many videos on how to do that. Some people just use surgical tubing, tied off at the end of the day. Crowned pulleys is what you want to look at if you're using flat belts to center things. Yeah, if you have the time, try to make them yourself using flat belts, experiment with it. But if you don't have the time, if you just want to move something, a small object, a small distance, just use timing pulleys that you find in the kit of part with the drivetrain pulleys. They're large belts with large pulleys that easily mount to FRC gear. That's free, paid by your registration.
Great, that's it for now. So
cool, yeah.
Thank
I'll
you.
get back to you. Right, so again, these are the machines that I thought notable to discuss as they combine lots of positive elements of the things we just discussed. I don't have any particular bias towards these teams. These are just ones that I thought were interesting of note that I'll discuss. This is also the last section of the presentation, as it were. So yeah, here we go. Right, Team Orange again. Their 2019 robot is quite a work of art. It's got the pneumatically deploying ground intake. It's got a turret, a 2-stage elevator, a 4-bar climber. The entire robot goes up on quite a precarious 4-bar mechanism. I dread to think of the gearbox that drives that thing. It's got a pneumatically deploying intake that launches out as well as being able to shoot. Oops, as we'll soon see. Yeah, so top roller pickup with a pneumatic deploy, great method. If you want to pick up a ball, good way to do it. Dual roller launcher on a pneumatic extending arm. The extending arm is not required, but obviously it does a good job. I know that 254 just used their arm mechanism by lowering the elevator and extending the arm at the same time. Very precise, very versatile. Let's have a look at how it works. There we go. And we'll see the pneumatic arm extending just because it's cool, no other reason. Right, so as we can see from here, they're very easy. They sort of, yeah, like with our 2019 robot, able to pick up the ball very well, but they hand it off to those rollers, which allowed them to shoot it very precisely and accurately. That extending arm is great. I will, unless you really know what you're doing, I wouldn't make one. It requires, yes, the blocks in tube, sort of, I couldn't make one without, 2 months and a high budget. But there you go. That's definitely a machine to look at for a very complete intake and scoring mechanism for a ball. So you can definitely use cubes for this sort of thing, but obviously you probably just use the dual rollers to pick it up at the same time. All right, here we have Crescent Robotics. This is Team 610. They're very, very nice robot reveal style things if you're ever trying to show someone FRC. The intake is dual sort of compliant rollers that just use 8-inch pneumatic tires with a roller on the bottom to sort of pick up the cube and pass it in. Self-centering, durable. It's very, very simple. Great way of doing it. This is for 2018 with the cubes. The arm is just a single hinge on the back, you'll see in the video. Allows for lots of adjustability and aiming. It's very simple, it's very durable. They use an electric drive with a gearbox and chain sprocket reduction. They don't use any cylinders or linear actuators. I guess that's how they chose to do it, and that's no issue with that at all. Obviously works quite well. And the last one is one that probably is not applicable for as many Australian teams because of how they did it. But their climber uses a 4-stage stack of square tubes with bearing blocks, and it sort of sits within itself. I know Project Bucephalus did something of this similar style this year. Large extension ratio, it's very, very compact and quite strong, but it requires some complex machining capability to do it well. And it can get quite heavy. Again, for Project Bucephalus, I know they had to put a lot of holes in it to make weight. But let's see how that ends up working. Again, sorry for no sound, but it's how it is. I'm sure you can look up the reveal after time. There you go. So I believe they have a pneumatic cylinder that also pushes out the cube and 2 rollers to sort of launch the cube. Again, quite a complete mechanism with a compliant intake, a straight shooter, and infinite variance within their range of motion with that arm mechanism. And obviously very simple, very durable. And let's have a look at the climber again for those who feel they're up to the challenge. So that one obviously is a mechanism of ropes and pulleys in order to get that. That's a cascading style climber because all the stages go down at the same time. You can sort of do something similar using the tubes that I described before. If you don't want it to be load bearing, using PVC pipe within each other and just ropes running inside and some low friction blocks, nylon or something similar, can allow you to extend very high, place a hook that then is released and then used to winch yourself up. The 118 They had an EveryBot, which is a sort of machine that someone can make for less than $1,000 and the kit of parts. They had something similar. So it's a similar style, large extension ratio with PVC. It's very light, but it's just not very load bearing. So do keep that in mind. You'll have to figure out some other way to take the weight of a robot. And now for the last robot that we're going to have a look at is one on our own home soil, is the Drop Airs. In 2017, they had a 2-axis gear placer. The entire mechanism slid left and right across the robot, as well as shooting out forward and backward. This enabled pretty much full range of 2-axis motion, considering the game object had to be placed on the little spring quite precisely, and using automation with vision. Very impressive to see. Haven't seen this any other machine actually, besides the Drop Airs in Australia. So all kudos to them for actually getting it done and doing it well. This is an example of taking 2 linear mechanisms and combining them perpendicular in order to get a lot of motion range and a lot of precision. And so yeah, let's have a look at how that works. There we go. So that was a bit violent in the end with the pneumatics. From my understanding, they were running full pressure on those cylinders, which sort of spoked out. So not the safest of all things, if I am correct at that. But yeah, so you can see that was actually completely autonomous. So again, very impressive that they did that. So yeah, this is a bit of a more complex way to do things. You sort of need a linear slide to get that left-right motion. And then the bit was pneumatic that sort of shot out and released. But again, a great use of taking 2 linear mechanisms, combining them with a little bit of software sprinkled on top to create probably the most impressive gear placing mechanism that I saw in 2017. So to completely wrap this up for the last round of questions, I believe, there are many ways to complete a game task. These are all examples. There are some that are more optimal than another. But the reason lots of different machines end up on the going to worlds and actually succeeding is because picking the right mechanism is one way, but implementing it properly is more important. Yeah, if you can take a mechanism, flesh it out, experiment, improve, it can perform just as well as the team with the water jet that did the design that everyone else did. It's down to prototyping, it's down to the entire machine as a whole, and obviously performance on the day is a very complex thing. You can't predict that, but pick a mechanism that you believe will work, go with it. Just because they did something else and they've performed better in the past does not mean it's going to be more successful. But make it as simple as possible. If it has less moving parts, if it has less ways of failing, if it's smaller, it doesn't have bits sticking out all over the place. If there's less ways for it to break, it means it's going to work more often. And it means there's less bits to handle, less literally moving parts to take care of. And at the end of the day, stuff is to be run with software. It can help simplify that. Better software can make a more complex mechanism, like with Code Orange. They had a turret, an elevator, and an arm. Obviously, software had to run all that. But you need a lot of good software in order to have a complex mechanism work. But one should not rely on the software if they can avoid it. Good mechanical design is simple mechanical design at the end of the day. Combine mechanisms if you can to reduce their complexity. Our team this year, our intake pneumatically extends and retracts. That is also what feeds balls into the indexer, the injector, which goes straight to the shooter. Balls sort of sit when it's out, it sort of sits in a hopper style thing, and a sort of wheel runs to pull it into the indexer and the shooter, and the intake extends and retracts to sort of just feed them in to the injector. So that's the way we have one mechanism that does both things for not much extra weight. It means it's simpler, it means it's lighter, it means it'll be cheaper. At the end of the day, that might be the be all and end all for certain things. Definitely try to combine things if you can. Some teams use their intake, the ground intake in 2019 to grab on and lift themselves up onto the hab. That's a great example. It requires one to have quite a good gearbox, quite a good mechanism. But at the end of the day, that extra weight you put into that is probably going to be less than a completely separate mechanism. Also, if you make that one mechanism reliable, it's a lot easier than making two mechanisms reliable. Testing and prototyping is paramount. especially if you're trying to get any mechanism to work. You need to test it, you need a prototype, see which mechanisms work well, then decide on one and then make that one work before you try to change. If it's not working quite as well, put the effort in with what you know, try to get it to work once you've devised ones that are sensible. Yeah, that's more of a prototyping talk. I know that someone did that last week, so I'll leave the rest of that to them. But yeah, test, prototype, try things. And yeah, explore different ways that a mechanism can be used. Just because, you know, a top roller doesn't work super well on a cube, you know, there might be a new game object, a new mechanism in the future that might work well for. I know that Bomb Squad, Team 16, their ground intake roller this year, 2020, they sort of angle it up and put it on the corner of the color wheel and rotate the color wheel just with their intake, with no extra actual mass or complexity to their machine. Try things. If you can shoot a ball with a catapult or you can shoot a ball with a shooter. And then, you know, a catapult would probably launch a cube and a disc and a ball, just, you know, as a roller shooter would. Again, that's someone else's talk. I don't want to steal what they're going to say. So one mechanism can do many things, just as there is many mechanisms for one thing. As you can see in the picture on the right, we've got a ramp bot. And I know this was actually intentional. They got little flaps that sort of have to be down to grab onto the third hab level for a robot to get up there, and they weren't working. So if it doesn't work for hab level 3, there's a decent chance it'll work for hab level 2. So that robot did a bit of a Hail Mary there. They did land on level 2. They did get those points, and the robot still works at the end of the day, from my understanding, without much damage. The entire mechanism sort of shook up and down. The information is at the bottom there if you wish to watch the match where that occurred. But yeah, even if it's a silly idea, at the end of the day, it probably can end up working out if you put the effort into making it to something practical and particularly reliable. So that's the end of my ranting, as it were. If there are any more questions, I'm very happy to answer them.
Hi, that was awesome. We have one question. Does your team have a process for choosing one mechanism over another?
Right. So I'm the mechanical captain for my team. So a decent number of the decisions made by myself. Obviously, we split up into a couple of teams. When we make it, there's a new challenge and there's a new robot to make. If there's a game released, again, I'll use the example of this year's FTC game where they're shooting little discs. You see it there, recognize it, like learn the previous FRC game is what happened. Recognize that that's a disc. Back in 2013, they were shooting discs too. You got an entire year and thousands of robots as an example of what worked and what didn't work. So if you don't have any immediate ideas, pick out ones that did function fairly well, obviously to the degree that you're able to manufacture. Then trial them. Don't just do something because a good team did it. Because, again, as I said before, a good mechanism is half of it. A good team will make any mechanism work for the job as long as it's reasonable. So they spent their time to pick one, and then that's half the process. Making it work is the more important second half. So we look at previous mechanisms, we decide which ones are good, we do a little bit of prototyping and experimenting, and then generally we decide on stuff pretty quickly, and then it's mostly making it work. So step one, have a look at who's done it before, if there's anything we can pick up and get a nudge from, then prototype and test it, and then improve on it as time goes on up until competition.
Awesome. Well, that was absolutely fantastic. A lot of great information. I think that we have a number of people watching, and so thank you so much for putting this together.
No problem.
Again, this is James. He is from the Blue Flamingos.
Yes.
We also need to do a quick shout out to IC Robotics, to Ian, who's been monitoring the chat and making sure that everything works behind the scenes tonight. So thank you, Ian. And I don't see any further questions. So have a great night. Thank you again. And we'll catch you next week.
Okay. Good night, everyone.